Hey guys, let's dive right in. We are still talking about potential energy curves, and specifically in this case, we know that force is equal to the change of potential energy over the instantaneous change of the potential energy over the position. And how do we know this? Well, we know change in potential energy is equal to negative work, because if we think about it, work is equal to kinetic energy also, but if there's more potential energy, something has the potential to do more, the change in positive potential energy means that that object lost motion, or they lost kinetic energy. If they lost kinetic energy, that means they lost work. Thus, the positive change of potential energy equals to a negative change in work. And using that, we can also substitute with K. Thus, we get Ku is equal to K, which is equal to 1/2 mv squared. And remember, it's not equal to just K, but it's equal to K times change of X. Or if we know the force done with X times X, integral of that, but since 1/2 mv squared, nothing in this thing changes at all, the force will remain constant. Does that make sense? Since when we define velocity at position X, it's in terms of the two energies. Okay, this is something we will come back to. Page 199. Let me just write it down. Okay. And then using this equation, we know F is constant, we can take it out, therefore this also becomes just a change of X, because of the two integral bounds is what it's going to be. So it's just going to be a negative change of X. Alright, because it's equal to work. That makes sense. And then putting this all together, we get negative force X, change of X, and then plugging this in with 1/2 v squared, change of X, so U. Simply just also keeping this f of x, actually, I guess that's what they do. Put this over, these are the small changes over time. So we can take the derivative and we just get dx du is equal to f of x. That makes sense. And this is what we do over small displacement change of x. So this is equal to this. Specifically as we take the limit. And in the specific equation above, when we take this to be 1/2 kx squared, we get this fx equals negative kx, which is the ideal spring Hooke's law. With this result, we can appreciate the oscillatory nature of the system whose energy curve is sketched above. If x is positive and not greater than x0, then ux is increasing. Right? then ux is increasing. X is positive. So when you think of a spring, right, if the position is positive, then the potential energy is increasing because it has more potential to go. But since it's in the positive x direction, u of x, we know that the force will be going this way, which is in the negative direction. It'll be a negative force. Okay. Furthermore, if x is negative and not less than x negative 0, then u of x is decreasing. So if it was compressed, u of x is actually decreasing because the potential energy compared to the 0 line is less. So even though the magnitudes might be the same, it's always to a relative free 0 line for a potential energy. Thus, yeah, that's what it's going to be.